Hello, everyone. It's my honor to give this talk, and thanks for all the organizers. Give me this opportunity to introduce the first results. Just come from the commissioning round of PandaX-4T. Okay, I come from. My name is Xiaopeng Zhou. Come from the Beihang University, and I'm collaborator of PandaX. My slides is focused on the WIMP. Okay, the most famous dark matter candidate. And I just let the other candidate here in with this plot. Yeah, yes, and we can also search axion also at the same time in PandaX photon. But this topic, the topic of this slide is focused on the web. Okay, and first, let me introduce PandaX project first. PandaX is a series of xenon-based rare event detectors, and it's formed in about 12 years ago. The first stage of PandaX is PandaX-1, 100 kilogram liquid xenon for dark matter detection. And then after PandaX-1, we just started PandaX-2. And for now, we are running the PandaX-4T at CGPO2, China Jinping Underground Laboratory. And at the same time, we are constructing the dedicated non-neutrino double beta decay detector with enriched xenon 136 TPC detector. Okay, hopefully we will see the result in the near future. And for now, we have collaborators from about we have about more than 50 collaborators from about 20 institutions. And that's all for the introduction of PandaX. Now, let me just give a simple review on the TPC technology. Okay, thanks to the previous speakers, they have introduced this technology in detail. Let me just show you the lights. Okay, this is the first signal happened in PandaX-4T. We have recorded. Okay, this is a typical alpha decay events with a small decay. Sorry, not decay, with a small z index. Okay, it just happened beneath the gas phase. You can say S1 as the first slides, and a delayed scintillation, we call it S2. Based on S1 and S2, we can do many things. For example, we can reconstruct the 3D information, and we can also have a powerful discrimination on nuclear recoil and electron recoil. And also, we have some other advantages. For example, we can perform also like a non-neutrino double beta decay detector with unenriched xenon, with natural xenon at the same time. And okay, this is the typical waveform. This is just a waveform recorded for the first event. This is S1 and this is S2. And okay, so you know, as a rare event detector, we must shield all the background as much as we can. So first, we put the detector underground in the deepest underground laboratory, CGPO2. And then we put the detector in pure water to shielding the gamma rays, the neutrons from the rocks. And finally, the PandaX-4T contains about 6 ton liquid xenon, and it can perform as a detector and at the same time perform like self-shielding materials. Okay, on the right bottom, we have the TPC figure. You can see we have about 500 3-inch PMT2 monitoring every signal in the detector happened during the data taking. Okay, I will just show you some pictures when we assemble all the TPC. This is the TPC. You can see the size, just a similar, a little bit smaller than Xenon N-Ton and LZ. And this is the picture for all the systems. You can see cryogenics, DEQ, and circulation, and emergency recovery system. Okay, and this is the bird view picture for the water shielding. The circle in the middle is the vacuum vessel for the TPC. Okay, then let's see what we can do in PandaX-4T. Okay, this is a calibration used in PandaX-4T. We have trypton 83 injected into the detector, and it will decay with cassette gamma rays. Okay, the typical energy is 41.5 keV, and you can see the energy resolution is pretty good. And using the calibration data, we can calibrate the uniformity in the whole detector, because the krypton is supposed to distribute evenly in the whole detector. Okay, and you can see the S2 and S1 RMS in the finished volume is pretty good. And we can also correct this number in the following data processing. And let me show you the drift. Let me show you the extraction field. Okay, one key parameter for describing the S2 signal is SEG. It means the single electron gain achieved by the proportional scintillation. And you can see in PandaX-4T, the SEG number is around 20. PE means photon electron per electron. Okay, and the extractor efficiency is about 90%. I missed the number, but you know the efficiency is around 90% for extraction efficiency. And we also have very, how to say, a uniform distribution on the SEG. It means the extraction field is pretty good. Okay, and let me show you the energy reconstruction. The energy reconstruction is a linear combination of S1 and S2. The efficiency parameter of a PDE means the photon detector efficiency, and the extractor efficiency of electron can be fitted in the so-called dog plot. The left one is the dog plot. From this figure, we can derive the PDE, EE, and EE at the same time, given we have the SEG in the previous fitting. And so combined with all these parameters, we can have the energy reconstruction information from S1 and S2 bottom. Okay, and I just showed the linearity of the energy reconstruction. The derivation is controlled within 1%. The red one is used for dog plots, and the blue one are just the cross-check peaks happened during the neutron calibration. And I listed the key parameters below. Okay, you can see. Okay, the extractor efficiency is listed here. It's around 90%. Okay, and we also carried out several kind of calibrations. For example, you know the WIMP just likely to perform like a neutron. So neutron calibration we call is the 1K procedure you must take, and a neutron and all WIMP will, all neutrino will generate a nuclear recoil. And we use DD calibration. DD means the neutron generator, and combined with the MB calibration. Based on this calibration, we can derive the the light yield, the charge yield, as well as the fluctuation in our signal model of S1 and S2. We can just translate it into S1 and S2. Okay, and for electron recoil, we also take the famous radon 220 calibration. Okay, and we using this calibration, we have built the signal model for electron recoil, and at the same time, we have one key parameter. We call it a leak ratio. It means the electron recoil just leaked into the typical nuclear recoil region, and the ratio is quite small. It's 0.4%. Okay, and the data and the model just agree very well. And based on the calibration, we can have our efficiency. Okay, we generally speaking, we have divided our efficiency into two parts. One is quality cut efficiency, and one is reconstruction and detection efficiency. Okay, the combined efficiency is the red line, and I will just show some basic quality cuts on S1, S2, and time to previous large signal in the right. Okay. Generally speaking, we have a plateaued efficiency at 40 keV about 90%. Okay, and okay, I have talked what our detector can do, and what are our detector resolution and reconstruction, and another key parameter is the background level. Okay, let's see. The dominant background for PandaX-4T comes from the radon 222. Okay, just similar to Xenon 110 and LZ, and also the Xenon N10 across. And we have improved 6 times from PandaX-2. Okay, and also krypton background is a normal key problem for the next generation detector. The krypton level is estimated to contribute 50 events in the final data sets. Okay, and we also have some research on the Xenon 137, 127 signal. It will generate a 5 kV signal in low energy region, and the expected background from Xenon 127 is estimated to be 8 plus minus 1 in the final analysis. Okay, we also have some other surface background based on the radon properties. It's specifically it's lead-210, and the level is also well estimated, and also the neutron is very important background. We have built several methods to estimate the neutron background, and in the final data set, the neutron background is estimated to be 1.2 events during the whole data taking used in the final analysis. And we also have
1 minute to go.
Okay, a key background is tritium. We found the tritium in PandaX-4T. We believe it's originated from tritium calibration at the end of PandaX-2, because we have reused all the xenon from PandaX-2, and we have built several methods to remove it in the near future. This is the whole table for all the background, and based on the data we have, and we have all the data opened analysis in the final results, and we have give our results using 0.6 ton years exposure, and the sensitivity improved by 9 times, and our limit is a little bit better than Xenon 110, because the the data from PandaX-4T is some kind of downward fluctuation. Okay, and this is the summary. And given because of the time, I will just neglect the summary.